Thanks for clicking. Welcome to another Nargilus production. Today we're going to be talking about concavity. Concavity is the way that we describe mathematically the shape of a curve. Okay, so we're going to explain to you what concavity is, what shape a curve can have, and then how you actually go ahead and algebraically calculate the concavity using a function. So it's actually something that you should be very familiar with. Okay, so let's talk about concavity first. Concavity is, by definition, the shape of a curve. So let's take a look. Here is a curve. I'm going to draw something for you, and I'll call it f of x. I'm just going to draw it here on the picture. There we go. All right, there's my curve. I'm going to call this f of x. Now, you can see that what happens is, if you look from left to right, the shape of the curve, right, changes kind of in the middle here. So my curve looks like a U. It looks like a parabola that opens up. And then all of a sudden, at some point, it kind of switches and looks like a parabola that opens down, right? So there are two types of concavity that a curve can have. A graph can be concave up, which it is here in this region. Simple way to remember, concave up. Okay, we'll define these a little more specifically in the next slide, but the graph is concave up if it looks like a U, it looks like a parabola. Or a graph can be concave down, if it looks like an upside down parabola. All right. So it can be concave up or concave down. Concave up looks like a U. Concave down looks like an upside down U. Now, at some point, this graph changed. It was concave up, looked like a U, and then at some point it switched over and became concave down. Maybe in this case, maybe right about here or so. Okay. This point has a special name as well. This point is called a point of inflection. All right, point of inflection. Okay, the points of inflection are the detectives of mathematics. All right, they are the detectives of mathematics. There are PIs. Okay, take that one to the bank. That's a winner. All right, so we have a graph can be concave up, it can be concave down, and when the graph changes from concave up to concave down, there's what we call a point of inflection. Now, it doesn't matter which way a graph changes concavity. If it changes from up to down at a point, it's a point of inflection. If it changes from down to up at a point, it's still a point of inflection. It's got the same name. Okay? All right, so let's define these words a little bit further. So, again, concave up. All right. So this is concave up. It looks like a U. So a more formal definition is the graph is concave up if the tangent lines of that graph lie below the curve. So if I challenged you and said, hey, draw some tangent lines in on this graph, you would draw them like this, right? Okay, all of the tangent lines are below the curve. All right. So a function is concave up if if the slopes are increasing. All right, and you can actually see that here. Take a look. Okay, I just drew a bunch of slopes. I drew 6 of them. But if you look from left to right, look at the slopes. The slopes are very negative. They get less negative. And then they get positive, right? F prime is a fancy way to say slope of tangent line. So the slopes are very negative. They get less negative, closer to 0. Then they get positive. So the slopes are increasing. F prime's increasing. So F is concave up. Okay? A graph is concave down if it looks like an upside down U. And when it looks like an upside down U, you would draw your tangent lines above the curve, right, on top. And now you can see a function f is concave down if f prime is decreasing. So if the slopes are decreasing. So you can see that here. The slopes start very positive. They get less positive, the slope of the tangent line. Then the slope gets negative. Then it gets really negative as it goes. All right, if f prime is decreasing. Now, again, there's a PI, or point of inflection, is a point at which the curve changes from concave up to concave down, or concave down to concave up. It doesn't matter. We don't distinguish points of inflection like we do relative mins and relative maxes, okay? Because relative min, the graph is decreasing, then it's increasing. Relative max, it's increasing, then it's decreasing. Points of inflection, or PIs, are just points where the curve changes concavity, from down to up or up to down. I don't care. Doesn't matter. All right. Now, we need to be able to algebraically figure out where a graph is concave up and where a graph is concave down. To do that, we actually already have an idea as to how this might work. Because a function is concave up if f prime is increasing. But if f prime is increasing, then I know something about f double prime. Think about it. First derivative test. When f is increasing if f prime is positive. First derivative. F is increasing when f prime is positive. Well, if f prime is increasing, then f double prime must be positive. A function is concave down if f prime is decreasing. Well, think about it. When f is decreasing, f prime is negative. That's what my first derivative test says. So if f prime is decreasing, then f double prime, the next derivative, must be negative. This kind of literally sounds like the first derivative test, but not using the first derivative, using the first derivative with the second derivative instead of the function with its first derivative. Okay, so now to find potential points of inflection, if f double prime is positive, f is concave up. When f double prime is negative, f is concave down. To figure out where the graph goes from concave up to concave down, or concave down to concave up, I would need to know where f double prime changed from positive to negative or negative to positive. Well, where would it change? Where the second derivative is equal to 0. That's where something changes over, a graph changes over from positive to negative or negative to positive. Okay? Or when f double prime is undefined. So now, having looked at all of this kind of information, hopefully you're thinking, well, wait a minute. We already know how to do all this, right? Except I did it with the first derivative test. When f was increasing when f prime was positive. F was decreasing when f prime was negative. But now you're just saying f prime is increasing if f double prime is positive. F prime is decreasing if f double prime is negative. And I looked for critical points here where f prime was equal to 0, right? That's how my first derivative test worked. Now I'm looking for where f double prime is equal to 0. Isn't that basically the same thing? Well, yes. Now you might be saying to yourself, hey, wait a minute. I bet I know what they call this. They call this the second derivative test. No, we don't. We call it the test for concavity. The second derivative test is something else, which we will get to. We just haven't gotten there yet. But it does have a reason for why that thing is called the second derivative test and not this. So basically what we're going to do is we're going to do exactly what you already know how to do with the first derivative test, but we're going to do everything with the second derivative. So we're going to find the concavity and points of inflection of f if f of x is equal to x to the fourth minus 12x squared. To do this, I need to go to the second derivative to find concavity. So the first derivative would be 4x cubed minus 24x. The next derivative would be 12x squared minus 24. So now, what am I going to do? How does the first derivative test? Well, I take the second derivative now, set it equal to 0. So I could take 12 out, 12 factors out. I'd have x squared minus 2 equals 0. So now I can split these and solve them both. 12 doesn't equal 0. That gives me nothing. X squared minus 2 equals 0. X squared is equal to 2. So x equals plus or minus square root 2. If I solve it, remember, to square root on both sides, you need plus or minus. So now, these are my two potential PIs. They may not be PIs, they might be. Okay, just like the first derivative equal to 0 would be your critical numbers. They could be a min, they could be a max, they might not be. All right, so now what am I going to do with these potential PIs? Well, I already know what to do. I'm going to put them on this number line here. I'm going to put negative square root 2 there, and I'm going to put positive square root 2 there. Okay, now what do I want to do? I want to take f double prime, and I want to test it so I can figure out information about f. So I'm going to test f double prime. I'm going to test numbers in each of these 1, 2, 3 test intervals. So I need something smaller than negative square root 2. So I know negative 2 is smaller than negative square root 2. We're going to test f double prime test. Oh no, let's put the test numbers up on top. Put them up here a little higher. All right, and then we can put the signs there. All right, so we're going to test up here. We're going to test negative 2. We are going to test 0, and we'll test 2, right? I know 2 is bigger than the square root of 2 because the square root of 4 is what is 2, and square root of 2 is smaller than that. So that's why I'm using 2 and negative 2. Okay, I want to test negative 2, 0, and 2 in f double prime so I can figure out stuff about f. All right, again, I do not care what the value of f double prime is. I only care whether f double prime is negative or positive, just like the first derivative test. So if I take negative 2 and put, well, 12 is positive. I don't care about this. This is always a positive. It's not going to do anything. The question is negative 2. If I put it into negative 2 squared minus 2, negative 2 squared is 4. 4 minus 2 is 2. That's a positive. All right, let's keep going. Put 0 in. 0 squared is 0. 0 minus 2, that's negative. 2 squared is 4. 4 minus 2, that's positive. When f double prime is positive, that means f prime is increasing. When f prime is increasing, that means f is concave up. So when f double prime is positive, f is concave up. When f double prime is negative, f is concave down. When f double prime is positive, f is concave up. So now, f changed from concave up to concave down. That makes negative square root 2 a pi. F changes from concave down to concave up. That makes square root 2 a pi. So now let's summarize what we have. F is concave up on the interval negative infinity to negative square root 2 in the union square root 2 to infinity because f double prime is positive. Done. F is concave down between negative square root 2 and square root 2 because f double prime is negative. F has two PIs. There's a PI at negative square root 2, comma. Now I need to find the y value at negative square root 2. So what y value do I want, though? I want the y value of f, because eventually that's what we're going to try to graph, is f of x. So f of negative square root 2 would be negative square root 2 to the 4th minus 12 times negative square root 2 squared. Okay, now every time you square a square root 2, you get 2, right? Square root 2 times square root 2 is 2. So if I do square root 2 times square root 2, that's 2. And then do square root 2 times square root 2 again, that's 2. 2 times 2, that's 4. Minus 12 times negative square root 2 squared is 2. So that's 4 minus 24, negative 20. Negative square root 2, negative 20. Why? Because f double prime changed from positive to negative. Okay. And then f has another pi at square root 2, comma. Now, if you do the math, you're going to get the same thing. You're going to get negative 20 because f double prime changed from negative to positive. And that's my answer. That's my analysis with justification. And that's a good answer. Okay. And that's all there is to this. You are literally applying what we did when we did the first derivative test, but now you're doing it with the second derivative, and it's giving you different information about f of x. Okay. And that's it. And as always, thanks for clicking.